My name is Professor Nasr Minallah. I'm a professor of computer science in the College of Computer Science and Information Technology at Imam Abdulrahman bin Faisal University. As you know, this talk is being arranged with the help of Saudi Aramco Cybersecurity Chair Seminar Series. We do invite distinguished people from academics and industry every month to share their experience with our participants. On the screen, you will see, let me share my screen. Just to give you an idea about our speakers we had previously. So you can see these big names, they have kindly agreed and delivered talks in our monthly seminar series. We also have those who are interested in these talks, we can provide you a link of our YouTube channel. So all these talks are available on the YouTube channel. Before I introduce Professor Srini Devadas, let me go through some housekeeping rules. We will divide this event into two sessions. In the first 40-45 minutes, Professor Srini Devadas will highlight and share his talk. After 40-45 minutes, you will have an opportunity to ask questions in the last 10-15 minutes in the Q&A session. I'll be glad to read out your question to the speaker. And at the moment, all the mics and cameras of the participants have been off. We will ask you if there's a need, you can then unmute your mic. Otherwise, please don't change the settings. At the end, we would like to see about your feedback, how we can improve this seminar series. So we will provide you a link of the survey that you can fill for us. And all those participants who are attending this seminar series will receive a letter of a certificate from the chair of the seminar series, which is Saudi Aramco Cybersecurity Chair. With this, now let me introduce Professor Srini Devadas. Professor Srini Devadas is the Edwin Sibley Webster Professor of Electrical Engineering and Computer Science at MIT in the Computer Science and Artificial Intelligence Laboratory called CSAIL. His current research interests are in the area of applied cryptography, computer security, and computer architecture. In 2021, Professor Srini received the IEEE Cybersecurity Award for practice for developing physical unclonable functions and the ACM SIG-AC Award for outstanding innovation for fundamental contributions to secure microprocessors, circuits, and systems. Majority of you who are coming from computer science and engineering background must have seen Professor Srini Devadas' talks in his lecture on YouTube. Just to share one of his lecture that I saw this morning, this lecture has been viewed by more than 4 million, had got more than 4 million views. So definitely those who have computer science background are already familiar with Professor Srini Devadas. It's really a great pleasure to have Professor Srini Devadas in our seminar series. With this, now I request you all to please join me in welcoming Professor Srini Devadas. Professor, when you are ready, please.
Great. Thank you very much for the kind introduction. I look younger than I look now. Unfortunately, I've aged like everybody else.
Thank you.
Excellent. Thanks so much for inviting me. I've shared my screen. I hope you can see my title slide. I think it's on full screen mode, and sorry, not yet. Now it's on full screen mode, and we should be ready to go here. So please interrupt if there are technical glitches, audio goes off, or what have you. I'm sure it'll be okay, but I just want to make sure. I mean, it is a little bit of a lack of feedback. I mean, if I were in the room with you, I'd know if you were confused or if things were going wrong. So yeah, so I'm pleasure to be here virtually, and I'm looking forward to telling you about research that was done primarily by my PhD student, Hanshin Xiao. And this work is on learnable encryption. And no, this is not a term that I would expect people to know because we just made this up. I mean, it's a title slide, and learnable encryption is a concept that we've named. It's related to lots of concepts associated with privacy preserving machine learning, and I'll explain that, but I'll also explain what exactly we mean here. And the basic problem here that we want to solve is one piece of the connection between cybersecurity and AI, which is that a lot of the times we are doing AI on private data. We want to infer private information, or we want to have private inferences, for example, medical diagnostics, whether someone has unfortunately a disease or not. And so there's outsourcing of computation on private data, which could be symptoms or medical numbers that come from the medical domain. So you don't have the capacity locally to run these very expensive machine learning algorithms. There's also proprietary aspects to the algorithms themselves. So there's privacy on the other side. So data privacy comes from the user, algorithm privacy, comes from the developer. And we'd like to resolve this conundrum, if you will, by saying, let's use cryptography, for example, to outsource private computation. So while the outsourcing agent can't really discover a lot about the data or maybe anything about the data, it can still compute on it and provide perhaps an encrypted result. And this encrypted result is only meaningful to the user who provided the data in the first place. There's techniques like fully homomorphic encryption, which is not the subject of this talk, but is related to learnable encryption, that solve this problem or attempt to solve this problem. And the main issue with this problem of using a fully homomorphic encryption on this problem, I should say, is computational cost. It's incredibly expensive. So one operation turns into billions of operations in the private world, in the encrypted computation world. And obviously, then you can't do expensive computation because it would take forever, essentially. So that's one way of solving this problem or trying to solve this problem. There's also techniques called differential privacy. There's really a slew of techniques where you take data and you don't transform it dramatically, but you add a little bit of noise to it. And there's a privacy argument associated with essentially anonymity, in the noise, anonymity through aggregation, that essentially says that, well, the individual, is protected. So if we're all trying to find, our average salaries or, something to do with information that is aggregate, each of us can contribute, our data, but with a little bit of noise. And if the only thing that's exposed at the end of this is the average, then the contribution that we've made to the average is obviously much less in terms of the privacy relationship. And that noise, kind of gives you a formal guarantee that even if you had not contributed, the average would still be the same. So differential privacy essentially says the contribution of an individual is being hidden, right? Though you're obviously giving away aggregate calculations. So I'm not going to go on and on about this. This is some context that I think is relevant before I talk about specific research work that we've done. But really, I want to leave you with there's many approaches and differing trade-offs. I'm just giving you one specific example of work that we've done in the last year, which has some advantages in some contexts. There's three dimensions here: the privacy guarantee, the computational cost, or the overhead, and then the utility. So sometimes, like fully homomorphic encryption gives you a very strong privacy guarantee with very large computational cost, but the utility is perfect because you're doing exactly the same computations in the encrypted world operation by operation as in the unencrypted world. Differential privacy gives you a weak privacy guarantee. Computational cost or overhead is low, but the utility can suffer because the noise would now make the data different, and therefore the results would not be completely accurate. In fact, you can't, there's a fundamental limit, as there is with learnable encryption, on how high the utility can be. You can't get perfect accuracy with differential privacy. So that was the context. So let me tell you what I'd like to talk about in a more technical way, deeper technical way. I want to talk about a transformation-based approach to learning that kind of draws from both of these worlds of fully homomorphic encryption and differential privacy, and then tell you what learnable encryption is. There's some limits to it. So there's really impossibility results associated with this that we want to be upfront about. And so what is the best that we can do? There's a specific approach that we call the dauntless approach. I mean, it was an acronym, but now it's turned into a name. We need names, evocative names for things. And so we picked this, the student picked this. And then I'll end briefly with trying to solve the even harder problem, which is a collection of us cannot exchange data that we own because of regulations or because we don't trust each other, but we want to collaboratively find aggregate information or even collaboratively learn a model that is better than the model that we could have learned locally. And how can we do that in a private way, right? So it's previously the outsourcing was just one client and server that was untrusted. Now there's 2 or more clients that don't trust each other but want to outsource and learn collaboratively on the untrusted server. And so that is sort of the last thing that I'll talk about. So not too many equations and theorems in this talk, but I just want to explain that optimization is represented using essentially this equation, and you're trying to find minimum usually, and usually you're trying to find a model that corresponds to samples. You usually assume a distribution P. So you could have a cat image labeled with cat, you could have a dog image labeled with dog, and this distribution comes from the distribution of animal images. And so that's all there is to it here. And usually there's something called notionally the generalization error that we want to minimize. And so this is a theoretical construct that essentially says, I'd like to learn a model such that if I get a new image that I should be able to recognize it as a hippo or an elephant or what have you with perfect accuracy. That's our goal. And in order to do that, usually we solve an optimization problem where the model that we're trying to learn is f of x that produces y, and we are saying that the loss associated with the f of x and y is the correct label, and f of x is the predicted label. So you'd like it to be y, but it's not necessarily y. And if it's y all the time, you're done. You've solved the problem. But if it's not, then you'd like to minimize the error, and you use different loss functions for that. Now, this generalization error is a theoretical construct, and we don't know what new images we're going to get. So usually we measure empirical error associated with a test set of images that correspond to these xi's, and there's n of these, for example, or there could be fewer of them. And you say, I'd like to minimize the loss that's here. And so the notion of transformed learning, again, mathematically, but I'm trying to keep this at a high level, is to say that all we have to do is take the labels, take the images and transform the images using this function t. And this function t, if it's a invertible or bijective function, the idea is that from a mathematical standpoint, in the transformed world, you can still try to find the minimum of this loss function L that is being run on f of t, x, and y, with whatever norm that you wanted to use. And if this was a bijection and or more strongly t were invertible, then there's a unique optimum for this problem. You can find that unique optimum even in the transformed world. So once you do that, every time you get, once you have your model, you only can use the model by taking your new image that you want to infer and running it through this transformation. So the idea is that, roughly speaking, and the essence of what I'm talking about is you can take your data, you can transform it using a one-to-one corresponding transform, and you can run on the transformed world, find an optimum, and this optimum is going to give you a model that is essentially an encrypted model if you view this transformation procedure T as a key. And you can think of T of X as the encryption procedure. And so if you took a T of X and you change the data very dramatically, then the question is, in this dramatic transformation of the data, can you learn an interesting model that has high utility? Obviously, if you added a little bit of noise and T was a differentially private procedure, I mean, this encryption is not very strong. The data looks kind of the same, and so there's a trade-off between the strength of the encryption and the capacity of learning. Right. So this is trying to put together the things I've talked about before. Fully homomorphic encryption has a very strong encryption procedure, but there's obviously, as I said, a computational cost associated with it. And so this trade-off essentially gives us a means of trying to create a framework that we call learnable encryption that defines what the two main constraints are. The two main constraints are, we want learnability preservation, which means that the model can be directly learned on the transformed data. And we want inversion resistance, which means that the person, the entity, the untrusted entity that sees the transformed data cannot invert the data and get back the private data, because obviously that would break the scheme. And so the impossibility result is that because we are asking for learnability preservation, any non-trivial scheme for learnable encryption cannot give you cryptographic level security, which is at the level of fully homomorphic encryption, right? The advantage with learnable encryption is that you can work directly on the transformed data, and because it's a bijection, the transformed data is roughly the same size as the original data, as you'll see in the example that we have coming up soon. But in the case of fully homomorphic encryption, you do get computational security or cryptographic security. So what is the explanation here? Why is this impossibility result true given the existence of fully homomorphic encryption? Well, fully homomorphic encryption is not something where you can run directly on the transformed data, in the sense that you cannot do meaningful inference on the transformed data, because you can't learn anything from the ciphertext, right? So, and there's a billion times overhead associated with fully homomorphic encryption, because you're going operation by operation. So there's operation by operation equivalence in fully homomorphic encryption, but there's no meaningful learning on the transformed data. And so bottom line is we cannot hope to have cryptographic security, but that doesn't mean that the game is over. We can have fairly strong notions of security that are in the information theoretic world. And I'll tell you of one specific example. And so the basic idea is that we want to have a definition of security that also comes from machine learning, right? So we want to say something like, let's talk about probably approximately correct. So PAC stands for probably approximately correct learning, which is a fundamental notion of learning proposed by Valiant 40 years ago. And that essentially says, I want the adversary's job, the same adversary who's actually doing my transformed learning and creating the transformed model for me, I want the adversary's job of inversion to be provably difficult from a pack learning standpoint. And roughly speaking, don't have to look at these equations in great detail, but roughly speaking, you have two parameters that are associated with hardness, epsilon and delta. So you're essentially saying that the adversary's job on approximating the original data to within epsilon should be difficult. That is, if you get really close to the data in terms of a guess, that guess has to have very low confidence, or you could have high confidence for kind of a very approximate, very rough guess. So what we want is epsilon to be large and delta to be large here for the adversary. So large epsilon means the adversary can only approximate with high error. Large delta means low confidence, right? So as you can see, we are using notions from machine learning to gauge the difficulty of an adversary while we are trying to do learning in the transformed world, right? So some interesting connections here, and I just wanted to point that out. So hopefully intuitively this all makes sense. The math is less important, certainly for this talk, but we've written papers, and I'd be happy to point you to literature that has the theorems and the proofs. But I hope everyone's on board with respect to what we're trying to do. All of this is over some data distribution, which is also kind of non-trivial to define, simply because you talk about images, you talk about distributions of cat images and what do cats look like, and then you look at animal images, but we have to approximate this data distribution in some fashion if you want to go prove our theorems, and I just want to point that out, and I won't really spend much more time on it. So the framework that we have is pretty straightforward. Here's a little picture. You have a user. The user is going to take data and perhaps pre-process the data just like they would for a machine learning task. And one example is mix up, where I'll talk about this in a few minutes, but you could take images and mix them up together. So you could take multiple images of cats and dogs and create, I guess, new species by mixing the cats and the dogs together. And then you transform the data using T uniformly. So all data gets transformed uniformly, and this transformed data gets sent over to the server. The server trains the model, and on the right-hand side of the picture is untrusted. And this model now is sent back to the user. And the most important thing is what I have to the left here, which I'm repeating at the bottom here, which is this transform model only makes sense to the person who knows the transform T. Okay, so you take this transform model, you send an original image through it. Nothing, it makes no sense. You're going to get gobbledygook at the output. The labels are not going to make any sense. But you take an image and you run it through the private transform T, and then you send it to the model, this model that was run on the transform data, which I called F. Then F of T x nu is going to tell you whether that image is a cat or a dog or what have you. Right? So you are doing this learning on quote unquote encrypted data. Right? So that's it. That's the framework. Not super complicated. The challenge is what is the security property and what kind of results do you get? Right? So it's going to be about utility, and it's going to be about security here on out. So here's finally an example. The way we're going to do this is by using a super simple transform that, interestingly enough, still has an information theoretic security property. So imagine that I have a square root of D times square root of D image of a cat, and similarly of a dog, right? And these things could vary, but usually we fix square root of D to be 100 pixels or what have you. So it's 100 by 100 pixels. Pretend that we have now taken this image and we've turned it into a vector that's associated with a 1 times D vector. So you're essentially end up getting a long thin strip. The transformation that we're going to do is taking this image x1, and we're going to multiply it by a D times D random matrix that could have entries 0, 1, or -1. So a huge number of possible matrices, D squared different variables that are unknown to the adversary, but known to the client who owns these images and is multiplying these images x1 times w. Now, you know your matrix multiplication. When you end up doing this multiplication, because it's 1 times d times d times d, you get a 1 times d output, which is shown on the right. And because w is random, you essentially get something that's gobbledygook, that it makes no sense whatsoever if you don't know what the image was and if you don't know what the w was. So obviously the adversary is going to see what you see on the right, but that is x times w or x1 times w, x2 times w. And not knowing x, i's, and not knowing w, it's hard to reconstruct, right? But we need to make that more formal, but that's the basic idea. To put it all together, the entire set of n samples of images, I'm going to do this, take the same w and multiply each image. You saw it for 2 images. So n times d times d times d is going to give me n times d. So unlike fully homomorphic encryption, the size of the data set, the ciphertext, if you will, is exactly the same as the original text. Now, if in fact you had what is called a chosen plain text attack, so if the adversary knows these samples and their correspondences, so if they know the left-hand side corresponding to the so-called unknown images, obviously it means that there's no privacy to the data in the first place, but I just want to point that out. If in fact, let me go back to this slide. If in fact you see what's on the right-hand side, this colorful image, the strip, and you know that this that colorful image came from a cat, and you know the cat, then you can solve, you know x1, that means you know x1 and you know x1 times w, then you can clearly solve for w. The chosen plain text attack is something that this cannot protect against, but you know it's not something we want to protect against. The whole point of this exercise was that we wanted to learn on private data. So X is private. If X were already public, what are you protecting? So X is private. W is private because you've chosen it randomly. And the only thing you're exposing is X times W, right? So it may be the case that the adversary knows something about your private data, that they're animal images, that they are images of iris scans or what have you. So there's some knowledge that the adversary has. And the formal challenge here that we have is if there's partial knowledge associated with X, and let's say W is completely unknown because it's randomly selected, then when an adversary sees X times W, what does the adversary learn? Is it still something that is hard to learn X from if you know a little bit about X and you only see X times W? And so that's where the pack learning theory comes in. I'm not going to spend a lot of time on it, but I will tell you about the one result that we have sort of at the top level. And that basically says that if there's entropy in the private data, you essentially get a difficult task for the adversary because entropy is in the private data is going to produce X times W that looks random, right? So that's essentially the overall picture. And so really the key question is, given an observation, which is this transformed data, can the adversary approximate with error smaller than epsilon at the input, the private input, with confidence, you know, at least 1 minus delta? And you want epsilon to be large and delta to be large, which means rough approximation with low confidence. And so essentially we can prove a theorem that basically says this. It says that if you limit the number of observation samples that the adversary has to M, okay, M as in Mary, and this M can be determined using our theorem or the application of our theorem, and it's related to the mutual information between the private samples X and XW, et cetera, but you can actually compute that with an application of the theorem. Then this theorem essentially gives you a relationship between the number of transformed samples that can be exposed to the adversary and epsilon and delta, right? So in this sense, it's similar to differential privacy, where in differential privacy, you add more noise, you get more privacy. And the only difference in differential privacy, by the way, is that high security and differential privacy, which unfortunately also uses epsilon and delta, same as pack learning theory, but the meanings are exactly the opposite in the sense that In differential privacy, you want epsilon to be small and you want delta to be small as well. Here, higher security in the pack learning world, which is something that we didn't invent, obviously, is high epsilon and high delta, because that corresponds to high error of approximation, which is what you want, and low confidence. So large delta, because we have 1 minus delta, it means low confidence. So upshot is you don't need to worry about the theory if you don't want to, but you have a relationship between, let's say you exposed 100 samples, you are going to get a super rough approximation with very low confidence given the 100 observations as an adversary. If you exposed 1 million samples, then at that point, the theorem says that your epsilon is going to get smaller, and so is your delta. So you better be careful. So that gives you a knob that you can use to determine how private you want your computation to be. And so the last thing I need to tell you about the algorithm itself is that it may be the case that you have a situation where you want to learn on both public data and private data. This happens all the time. You have a private data set, there's a public data set. Together, you would like to learn a model on this distribution that corresponds to both the public data and the private data. So in this case, because we're worried about this chosen plain text attack, what you have to do is you have to add entropy to the public data using the private data. So let's say the cat image is public and the dog image is private. So that's your dog, and that image is private. It turns out you can use data augmentation techniques, which we didn't invent, called mix-up, that essentially say, you can still do learning on these mixed cat-dog images. That's 0.7 cat and 0.3 dog. So you see what you see on the right with respect to this mixed-up image. But obviously, you can see, kind of the outline of the cat. You can see the cat quite clearly, and if you tilt your head properly, you can see the dog as well. So I'm not saying that this cat-dog image is private. I'm just saying that if in fact you end up taking this this mixed-up image and transforming it using T, which is this random W, then you're going to end up. I'm sorry, I didn't have a picture of that. You're going to end up taking this image that's on the right, and you're going to multiply it by W. And that is the multiplication by W is the only thing that the adversary is going to see. And so when you do that, you end up with a security property, right? So this mix-up, to be completely clear, is simply to accommodate some public samples in your data set that you want to use for learning along with your private samples. The only security that you get is from your private samples. Clearly, the public samples can't give you privacy because they're public by definition. So I'm ready to show you what happens when you run these experiments on taking a mixture of public and private images, transforming them using this W matrix, and sending them over to a server and learning a model. What happens to the utility, for example? This W is a very dramatic transformation, as you saw. You end up getting essentially random looking pixelated images that corresponds to these lengthened strips when you turn it from the matrix representation to the vector representation. But this works reasonably well. And so this table needs a little bit of elaboration. The first row of the table essentially says, let's take this MNIST data set and do non-private training on the MNIST data set, which has 60,000 images. Then you run for a while, for a few 1,000 iterations, 5,800 iterations, and you get 98.5%. So this is just handwriting recognition. It's a very simple data set. Now, when we do this mixing, two mix means that you took potentially 2 images, one of which was potentially public and the other was private, but they both could be private as well. You mixed them up, and then you ran the mix up on the, and then you transformed it. So it's transformed. So we're looking at the fourth line of this table here. You can also do this in the non-private way. So assume that you didn't transform it and you did the mix up. Well, you get 98.3. Sometimes you even do a little bit better. Obviously, that's a small amount of improvement. But mix up by itself in the non-private world doesn't hurt performance, right? It's a data augmentation technique. It's sometimes used to improve utility. The transformed world, of course, is new because we're taking this data and we're multiplying it by a transformed image, multiplying it by a W, and the transformed image, may not learn well. And so in that case, you're in a situation where you do almost as well, but not much worse. And so that's the good part about it. The utility dropped by 0.1, 0.2%, and that's a good result because you've transformed the data and you have a privacy property. Now the results don't look that great if you do things that are with more complicated data sets, and if you only use fully connected networks, right? The non-private training itself in the fully connected network world only gives you 50%. Okay, this is not a limitation of the private training. This is a limitation of the fact that on CFAR, which is a more complicated data set, you need to use a CNN, a convolutional neural network, in order to get 90% or what have you. But again, you can sort of match get the 50-55%, and you can get up there with the transformed learning. So all you want to take away from this slide is that you can match whatever you get in the non-private world, roughly speaking, in the private world as well, to within a couple of percent, right? But this is not a great result because 55% not particularly accurate, right? So what we'd like to take this transformation and generalize it to convolutional neural nets. And it turns out that the reason this doesn't work is that if in the CNN world right now, we have to improve this, is that the transformation, multiplication by W, is a very global transformation, as you saw. So the CNN is a local convolutional transformation, the convolutional layer, I should say. And so this global transformation ends up in the inputs, ends up causing a lot of trouble for learning. So how do we solve that? Well, it turns out you can tailor a transformation that mimics the convolutional transformation in the private world, and you can get much better results, right? And I'll explain this to you pictorially. So what is happening in convolution? You have an image that is square root of D times square root of D, and you're running it through a convolutional filter that is K times K, which could be 3 by 3 or what have you. And pictorially, what's happening is you're taking this convolutional filter and you're walking it across this image, and you're going left to right, and then you're going to go one row down or K rows down, and you're going to go left to right again, et cetera, et cetera. Pretend that every time you're doing this, that you're looking at this K times K window, and you're turning it into a 1 times K square row vector. And every time you do this, you're going to multiply this by a different K square by K square WI matrix, and you're going to get your transformed image. So the only thing that changed here is instead of having a single W for the entire image, I'm going to have many WIs that are each independently random that correspond to K square by K square random selections. All right. So again, details aren't important, but we're doing a different transform that multiple smaller random matrices. And if the stride is T and the convolutional filter has size K and the original image has square root of D by square root of D, then you're going to step through Q times in each dimension, and you end up with Q square different WI matrices. And the idea is that your transform now is going to take your data, which is X over here, and is going to multiply pieces of X as this convolutional filter walks through over X and produce this transformed image Z. And then you send it over to the CNN, and you can learn on this transformed image. But now you've done kind of a local transformation many times that is similar to the convolutional transform, and the learning works much better, right? So that's all that I wanted to say. The effective CNN input is changed, and the front part of the CNN is changed ever so slightly, but the rest of the CNN looks exactly the same. The 10 or more layers that come after it, or the 20 or more layers that come after it, it's completely unchanged, and the adversary runs on transformed data. And now the results look a lot better. Roughly speaking, focus on the column that is second from right, and you can see that the non-private training, does well at state of the art, 93%, 90%, or what have you on CFAR for the particular CNN network that we used. And obviously using a different network is possible and you can get better results, but that's not the point here. The point here is what would happen when you ran this on transformed data, transformed in this local way, as I described to you, and you more or less get pretty close within a 2 or 3% of the non-private training, which is a lot better. So now instead of getting 55% on the non-private data, you get 93%, and you're get up to about 90% on the transformed data as well, right? So this tailoring of the transform is important for the practicality of this approach. So the last thing I want to say is how can you take this approach and generalize it to the case that I mentioned early on, which was many of us have private data and we'd like to together learn a collaborative model, but we cannot exchange data with each other because of regulations or because we don't trust each other. Now we could have a third party or we could do multi-party computation to together choose the same transform matrix or the same array of transform matrices, the WIs that I just described to you. But this collaborative approach requires multi-party computation to decide on this transformation matrix, which has two issues. It is quite expensive to do multi-party computation. And also there's a non-collusion assumption that's associated with this, where you, if there's three entities that are doing multi-party computation, two of those entities could collude and destroy the privacy of the third entity. So this is not optimal because it's not as secure given this collusion assumption as before. Now, if individually we took different Ws, so I took my data, multiplied it by W1, and my friend Kurt took his data and multiplied it by W2, then the learning gets confused because the distribution of the data is really dramatically different. The transformed data came from two different transformations, and you don't get good results at all, right? So so you'd like to have somehow have different Ws that are unknown to each other. So me and Kurt don't know the Ws that we've chosen, but the learning is capable of working with these different Ws and still producing a collaborative model. And it turns out, surprisingly, you can actually do that. And I'll be very brief here, just give you the highlights using the notion of task augmentation, right? So what is task augmentation? Task augmentation is something that creates a cross-product task across two learning tasks. So the idea is that owner one has X1 and Y1 with the superscript 1, which correspond to labels of his cats and his dogs with appropriate labels. Owner 2 has maybe another set of animals, also cats and dogs, that correspond to his or her labels. And we'd like to create a composite task that is a concatenation, if you will, or the cross product is probably a better way of putting it, of the two tasks from owner 1 and owner 2. So the idea is that you take the cat image from owner 1 and concatenate it with perhaps the dog image with owner 2, and then you'd label this the cat dog image. A little bit different from mix up because you're keeping both labels sort of side by side, but you could clearly do that side by side, top and bottom, or what have you. So you create these composite images with composite labels, and you can do that. Anyone can do that. There's no privacy associated with this. The transform is not appeared yet, right? But you could do this on transformed images as well, and that's what we are going to do. So now you can take this composite task, treat it as a machine learning task, and you can learn a model for it, right? So this model now needs, in order to use it for inference, it needs a composite image. So you have a new image that you want to learn the label of, and what you need to do in order to use this composite model, and let's say it's me, I take this new image and I want to figure out what animal this is using this model. I take any or multiple images that came from Kurt, the owner 2, and concatenate them and essentially run it through, because I can only run this on the composite image, and I'd get 2 labels back, and I just look at the first image, and that tells me in inference whether the image I sent in was of a cat or a dog or a hippo or what have you. I could also run this multiple times, take my XNew and send it through with different images from owner 2, namely Kurt, and look at only the first label that comes back in each of these 3 invocations or 3 inferences and take the majority, right? So, so what is nice about this is that what I've described to you can work on transformed data exactly the same, with having the transforms for owner 1 being T1 and owner 2 being T2, and owner 1 does not need to know T2 and owner 2 does not need to know T1. So this cross product works just as well on the original images as well as the transformed images. So as you can see here on the right hand side, you see T1 XI and then T2 XJ, and then the labels that correspond to the appropriate images. So the server is going to see images from me transformed with T1 as the first part of the image, images from Kurt transformed with T2 as the second part of the image. It's going to also see in training, the composite labels. It's going to go produce its model. It's going to send the model back to both me, and it's going to send it back to Kurt. And when I get the model back, I'm going to essentially say, I have the model, I have XNew, so all the way to the left-hand side of the slide, I take XNew, I run it through T1. I don't know T2. So, but I have the transformed images, which have no sensitive data in them associated with owner 2. And so I can use those transformed images with my newly transformed XNew image transformed with T1 to find the label for it. And I'm only interested in the first label because that's the label that responds to my image, right? So the key, and this is the last thing I'll leave you with, is that each owner can independently run inference on the model using the transformed samples of the other, right? So you've now done collaborative learning. And so this works reasonably well. I mean, we still have work to do, but you can do better. Each owner can do a little bit better using the other owner's data, even though they don't know the other owner's data. So it's not as good as exposing the data to each other, or it's not as good as non-private learning, but it's better than doing learning on your own. So there's a benefit to collaboration, even though the collaboration was private. And so that's the last thing that that I have for you before I summarize. So I've showed you a way of doing learnable encryption that does not require, unlike FHE, does not require an operation by operation equivalence of the encrypted world and the plain text world. In FHE, every add and every multiply is exactly the same in the encrypted world and in the unencrypted world. Here, we're just looking at the final output, and we want the final output to have an interesting property associated with learnability. That is, we should be able to do inference on it. And transformation approaches, I didn't talk about computational cost because the overheads are fairly low. Transformed data, as I mentioned, is about the same size as the original data, and it's not 1 billion times bigger as it is in the FHE world. I also talked about differential privacy. I want to make one final comment about differential privacy approaches, which is they add additive noise and it directly impacts utility. We're also adding randomness here, but it's multiplicative randomness associated with the W vector. And it's this bijection, this is invertible matrix that doesn't necessarily create lossy transformed data. And so there's some deep questions here that we'd love to answer that we're really early days yet. This is very preliminary work. We've been working on it for a year. And hopefully, as we go further and, perhaps with collaboration with you and others, we can get to the point where we have, essentially a journey to the promised land, where we have, perfect utility. We can collaborate, in a beneficial way without exposing any information to each other, and also not exposing information to the server. So that's all I had. let me go ahead and really stop my screen share here so I can see people's faces, and it's a little bit easier to communicate. And I'm happy to take questions. I see there's questions on Q&A and chat, but I'll let the moderator here control things and decide what I should do here. So thank you so much for attending. And I hope I gave you some sense of what this work was about.
Thanks, Professor Srini, for a very detailed talk. We have received a good number of questions. So I think I will go through them one by one. We will give priority to those who are available present today in the session. So some questions are coming from the students, so definitely they will be not making much sense, but hopefully you will understand what they're asking.
I think they'll all make sense. I think they're all great questions. I mean, I saw the ones you sent. Yeah. So.
Yeah. So I'll go on the other order. I will take the last one first. We just received some questions, so I'll go with this order. The first question says, how strong quantum computers can encrypt, and how much time is needed to decrypt message using the quantum computers? I think they're asking what will be the role of quantum computers.
Yeah, no, it's a great question. So the cryptography in the quantum world, quantum cryptography is very, very different from conventional cryptography. And the reason for quantum cryptography is the motivation is that quantum computers can, if they are built to scale, which isn't true yet, they can break conventional cryptography. So then people say, well, what will happen if quantum computers are built? Well, we need quantum cryptography, or we need different notions of cryptography in the digital world. So there's no problems with speed of quantum cryptography, from what I can tell. These things happen at incredible speeds, but you have to be careful because it's an analog world, roughly speaking. I mean, that's not the best way of putting it, but that's the best way I have of putting it. And so, for example, quantum cryptographic algorithms, if you're running this over a link, and you're sending this information over a link, then this link has to be essentially an analog link, and so there's degradation on the link. So it's very interesting that some of these techniques, and this is not true for all the techniques, but some of these techniques essentially say that distance, physical distance, is a problem with respect to encryption. So I can encrypt, and it's easy to decrypt for someone who's close by geographically. But if I'm going from here to Saudi Arabia, then that encryption doesn't work because there's loss in this quantum channel, and therefore the person on the other side cannot decrypt, right? So it's very interesting where the limitation is not the speed of encryption or decryption, from what I can tell. And I'm not an expert, by the way, but I'm sort of an educated layperson. But it is the case that there's these other criteria corresponding to how far you can send an image, which is not true at all in the digital world. I mean, once I encrypt, I could send this to the moon. It could reach there, a day later or several minutes later, and that person on the other side can decrypt it, and just as well as a person who's received it, next door in Cambridge from Boston, or Boston from Cambridge, can decrypt. But this is far away. I mean, quantum cryptography, I think you can do quantum cryptography now. It has these limitations. I tried to answer the question as best as I could, but quantum computers that can break, RSA and can do factoring at scale are far away, right? So.
Now we will go to other questions. The first question says, when we have plain text in secret encoding functions, which one is good for the machine to learn quickly? I think it's about.
Sorry, you have plain text and secret encoding functions, did you say?
Correct. Yes.
Yeah. So that's a great question. That's a great question. So in our technique, it turns out that they're kind of equivalent to each other because there's a symmetric relationship. We took X and we multiplied it by W, and so the contribution of X and the contribution of W, that the X is the plain text, the private image, and W is the secret encoding function. So they're interchangeable, right? So in the context of my talk, it's the same, but in the context of conventional cryptography, really the game is you want to make it as hard as possible to learn the plain text. The discovery of the secret encoding function, it might happen, because of, for example, side channel attacks for extraneous things, or because there's some additional information that you have about the secret key because it wasn't chosen randomly, etc. So you're stuck with the plain text that you want to send. In the conventional cryptography world, you assume that the plain text, is you don't really make assumptions about the plain text, about the entropy of the plain text or what have you. You have to protect it against chosen plain text attacks. So it's a stronger notion that you need in the conventional world, as opposed to the talk that I gave. So perhaps this was a question for the state of the art in the conventional world. So that's why I'm answering it this way. So there's no constraints on the plain text. The game is about discovering the plain text, assuming that the key was chosen randomly. Given that I gave this talk, I just want to say that we make stronger assumptions about the plain text, the fact that it has some secret information in it, because we're looking at a constrained private learning setting, right? So I'll leave it at that. Hopefully that was useful.
Thanks. Yes. The other question says, do you think cloning machines will be a threat to human security? So this person is asking about the cloning machines, how it will influence the human security. I think this is the question.
Yeah, so this one, I'm not quite sure what was meant by cloning machines, but clearly digital machines, at some level, my laptop, is running exactly the same software and produces the same result as someone else's laptop. And so you can, clone in the digital world. It's cloning in the biological world, of course, is something I don't know anything about, and it has some serious repercussions, but it's obviously possible there as well. And in the analog world, it turns out it's actually hard to clone. Even when you look very carefully, any two integrated circuits that were fabricated even with the same digital mask are not exactly the same because of manufacturing variations. And so there's these things like device DNA and physical unclonable functions that I've had some, should I say, some contribution to, are things that you can use for security. So the fact that things are unclonable, even in the analog manufacturing world, can give you imprints of devices that you can use for security. Absolutely. So I don't think cloning in the analog fabrication world is easy, and the fact that it's not easy is actually useful for security, right?
Yes, so I think these are the students' question, and they are by cloning probably they are pointing to the robots and drones, etc. Because the other question is also in this context. So let me read out the question. The question says, are clonable machine able to learn as the time progresses, or they are only clones with no change from parents, which means no intelligence will be added in the next generation? So the question,
yeah, well, I'm going to have to
okay,
probably skip that one. It's not something that I know. I know very little about cloning, and you can imagine that if you obviously if you have machine learning software that is learning, and you start it up in Game of Life or what have you, it's entirely possible that the random path that it takes ends up with a different entity. So obviously, you're cloning something that's let's say, quote unquote, is in the fetal stage of its development, and I don't mean biological, in its early stage of development. And you can imagine that the random walk that it takes, to as it grows and ages, would end up in a different spot. So I would say the answer is yes, but I'm not sure I'm addressing the question. But that's my limitation of knowledge.
Right. Thank you. Yeah, the fourth question is a bit technical. It says, based on your experience of probably approximately correct security, does it produces better results for data security or not?
Well, that's certainly related to my talk. So PAC security is not as strong a notion of security as cryptographic security, for example, RSA or what have you. And I tried to say that in my talk, and hopefully that came across. but it has some advantages, and which is why we are trying to work on this, that corresponds to the utility, as you point out. When you create a transformation approach to learning using pack security as your basis, unlike, for example, differential privacy, which is also an information theoretic security notion, you can get stronger security, I believe, using the pack notion, and you can get potentially better utility. So in some sense, our competition is with the information theoretic world of differential privacy, less so with the cryptographic world, because we can't achieve cryptographic privacy. But the problem with cryptographic privacy is not the utility loss. You can get a perfect utility there. The problem is just computational. You just can't run it for large data. So, so these approaches of multi-party computation and fully homomorphic encryption, you just can't run it on anything other than tiny amounts of data, because it would take a million times longer. So if you take a second, it would take a million seconds, and nobody wants to wait a million seconds for getting a medical diagnostic back, even if it's private, right? You just, and if you go much further, you've moved on to a different world, if you will, metaphorically speaking, by the time you get your diagnosis from the doctor, right? So that doesn't work, right? But thanks for the question.
Thanks. Yeah, probably the last question, and after this we were gonna end the session. It's prayer time, so we will finish it in a quick 2-3 minutes time. This question says, is there any chance that AI improve the firewalls and cybersecurity in general? Absolutely,
absolutely. I think I alluded to this, I think, in our conversation, before the talk, which I'm not sure everyone was on at that point, but using machine learning to attack systems, and perhaps using generative adversarial networks to improve the security of systems, and this is a loop. So I really think that it's as I said, the symbiotic relationship, in the sense of you can potentially obviously do privacy preserving machine learning to protect your data. That's what this talk was about. But the other side of it is using machine learning to improve intrusion detection systems, to discover attacks. And also, like website fingerprinting, there's Tor, which is an anonymous communication network. It turns out you can use website fingerprinting using the state-of-the-art machine learning and actually de-anonymize people on Tor. And that work ended up improving Tor, because people went back and said, we better do things better in the Tor world as opposed to what we're doing now. And that's the case where machine learning improved security, I think, in this loop. There's a question here that says, have you tried to learn from encrypted data with AES 256? And the answer to that is, unfortunately, you can't do that. And it's similar to the fully homomorphic encryption case, where if you have strong encryption like AES with certain assumptions, obviously, as with anything else, you cannot learn in the encrypted world. And that is kind of the impossibility result with learnable encryption. And so that's a great question, which is, when you do strong encryption, it's hard to learn. And so in learnable encryption, we are trying to find a sweet spot where you have a pack security property, but you still can learn, right? You have learnability preservation as well as some form of inversion resistance. So that's exactly the conundrum here, right? Thanks for all the questions.
Yeah, thanks for taking the questions. So we are done with the questions. And with this, now I will invite my dean to kindly thank the guest speaker and participants and conclude this session, please. Thank you.
Yes, thanks, Professor Nasrullah, for the excellent moderation of this session. I would like to thank our speaker, Professor Srini, for joining us today, sharing his valuable knowledge. And I believe I'd like to also thank the audience for their interaction and making the session more valuable. I have just the topic is very interesting. Thank you, Professor Srini. I'm trying to think about we are moving now to the ubiquitous computing, the cloud computing, and how important that your data, when stored in the cloud and trying to be processed in the cloud. This topic will be very brief priority. My question related to the grid computing. Do you think that if we apply grid computing, this will solve the concern, or still the concern exists?
I mean, it may allay concerns. It may allow you to, metaphorically sleep a little better at night because you are not, giving away the entirety of your privacy to some entity that presumably is acting rationally, but you're paying them to act rationally. But they could be attacked. You're not just trusting the grid. You're not just trusting the entity. You're trusting with your data. You're trusting their competence. You're trusting the fact that they won't necessarily fall prey to an attack. So it's not that they're bad people necessarily, because we're all you're all on the same side. But this is an extra layer of protection that I think you can control because you're not just taking your identification information. You're not leaving your credit cards lying around. You keep them in your pockets. And so here, if you encrypted your credit card and your credit card was outside, but no one could get anything out of it, well, that's better, right? Because even if you lost your credit card, you're still okay, right? And so two factors, all of these things. I think we have to live in the world now. Unfortunately, I think where trust is going to be less forthcoming, right? And that's just the way things are. And it's also there's no physical proximity that's required here in this world for attacks. You have a situation where you could be attacked from anywhere and everywhere, and so I think this extra layer of protection is absolutely important, right? Yeah. So
thanks, Prof. Srini. Yeah, and I believe that's why the zero trust concept is now moving on. I believe.
Yes, absolutely. And
yes.
I think in order to get zero trust, you have to have layered approaches. I mean, one way it's certainly, and I think in my mind, that's almost mandatory, right? So it's yeah.
Yes. I believe by this would like really greatly thank you for joining us. It's an honor for the cybersecurity chair lecture series to have you in our series, and I believe it's adding a great value, and looking forward for more contribution, more collaborations with you.
Yes, absolutely. Thank you so much. Thanks for the invitation. Thanks for the hospitality. And I'm happy to do this again. So. Yep.
I appreciate that, and hopefully in person next time.
Right. Great. Thank you.
Thank you.
Bye-bye.
Bye. Bye.